We discussed insert and merge sort in our previous two lessons. One of the cutest little data structures that we've ever inherited is called the heap. And we're going to use the heap as an example implementation of a priority queue. And we'll also use heap to build a sorting algorithm called heap sort that is very different from either insertion sort or merge sort. And it has some nice properties that neither the insertions sort or nor merge sort have. But what I want to do is to get started with motivating the heap data structure regardless of whether you're interested in sorting or not. So the notion of a priority queue, I think, makes intuitive sense to all of you. It's essentially a structure that implements a set of S or set S of elements, and each of these elements is associated with a key. And as you can imagine, a priority queue is something where you queue up for something, you want to buy something, you want to sell something. You have certain priorities assigned to you, and you want to pick up the maximum priority or the minimum priority. You want to be able to delete it from the queue. You want to be able to insert things into this queue. Also, you want to be able to change priorities in the queue. So all of these operations are interesting operations that should run fast and for some definitions of fast. Obviously, we are interested in this asymptomatic theory or asymptotic theory, complexity definition of fast. In that case, we'll be saying doing this operation run an order in time, order log n time, etc. So in general, I think for the next few lectures, you're going to see a specification of data structure in terms of the operations that the data structure should perform. And those of you who have taken 6005, you will see that it's basically an abstract data type that's associated with these operations. So it's a spec for the abstract data type. In 6005, you had really spent a lot of time on asymptotic complexity or the efficiency of operations on the abstract data type. Here in 006, you will specifically use this ADT and specify the set of operations or methods in the ADT, and we'll talk about whether there is an order, n complexity log, n complexity, and compare the contrast and different ADTs. So today's ADT is a heap, and what is the set of operations that we'd like to perform on a priority queue? So we can use that to motivate the development of the heap, and those are insert SX. So you have a set of elements S and you want to be able to insert X into set S. You want to be able to make maximum of S, which is a return of the element of S with the largest key. And different from max of S is extract max of X, which not only returns the element with the largest key but also removes it from S. So you have a queue and the person in the queue was serviced. So the element in the queue was serviced and then removed from the queue. And finally, you can imagine changing the priority of a particular element X in the set S. And this priority, there is an associated key as we have up there with each element, and that key is called a K. And increase KSXK would increase the value of X's key to the new value K, and K could correspond to it. It's just called increase. Most of the time, you're increasing the value in maybe a particular application. You could have suddenly a decrease key, and you would have to know what the previous value was. And it's just a matter of exactly what operation you want to perform. You could call it update or increment, whatever you like. I'm going to spend most of the time here talking about how to maintain a rep variant or invariant of this data structure called the heap that allows you to do these operations in an efficient way. And we'll talk about what efficiency is, and we'll try to analyze the efficiency of these algorithms that we've put up. So let us talk about a heap. A heap is an implementation of priority queue, which is amazingly an array structure, except that you're visualizing this array as a nearly complete binary tree. And what does that mean exactly? Well, the best way to understand this is by looking at an example. We got 10 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So here is my array of 10 elements, and the elements are 16, 14, 10, 8, and 7. So some set of elements that are in random order, clearly not sorted, and I'm looking at the individual individuals or the indices and I'm looking at the elements, I'm going to visualize this as a nearly complete binary tree. It's not a fully binary tree because I only have 10 elements in it. I would want to have 15 elements to be a complete binary tree. And we want to be able to do this in the general case of an arbitrary size array. So that's why we call the nearly complete here, or the tree. So what does it mean to visualize this as a tree? Well, index 1 is the root of tree, and that item is the value of 16. So what I have here are indices 2 and 3 are the children of 4, 5, 6 and 7 are the children of 2 and 3. And 8 and 9 and 10 are the children of 4 and 5 in this case. So that's the picture you want to keep in your head for the rest of this lecture, which will be continued in the next part.